Hello, my name is Ori Stiglitz, and today I'm going to talk about speeding up online POMDP planning via simplification by Vadim Indelman and myself. All around us, autonomous agents are emerging. Decision-making under uncertainty is a fundamental problem in AI. It has many applications such as active SLAM, autonomous navigation, and many more. However, it is computationally expensive. In this work, we tackle the challenging setting of planning under uncertainty and present a novel approach that demonstrates how we can speed up the planning session while assuring the same solution as the baseline. To describe the problem and account for the existing uncertainty, we assume the mathematical model of a POMDP. Instead of planning over the agent state, which we don't have access to, the agent maintains a posterior distribution over the state, which is commonly known as the belief. Using the belief, we can account for information theoretic rewards, such as differential entropy. These rewards can be very useful when a planning task has no predefined goal, such as search and rescue missions. In planning time, the agent can plan into the future using a belief tree, where future belief nodes along the tree are generated by having access to the observation and motion models. Each belief node induces a reward. The planning goal is to find the policy that induces the highest cumulative discounted reward. As our contribution, we introduce POMDP simplification as a complementary approach to existing POMDP planning algorithms. The approach is meant to speed up planning problems with information theoretic rewards and non-parametric sample-based belief representation. To demonstrate our approach, we derive novel bounds over the particle-based approximation of the differential entropy. We then show how these simplification-based bounds can be merged into a general sparse sampling planning scheme, speeding it up significantly. The term simplification refers to a line of works by Professor Indelman's research group that focuses on relaxation of the decision-making problem, while ideally assuring the same solution as a non-relaxed problem. We focus on this work on belief node simplification. When the belief is represented as a set of weighted particles, we take a subset of particles in order to represent what we denote as the simplified belief. Instead of calculating expensive rewards over the entire belief, we consider a subset of particles and calculate simplification-based bounds over the reward. The bounds can be generalized to bounds over the value function. Specifically, we've derived novel simplification-based bounds over the differential entropy approximation by Boyles et al. Our bounds are highly functional with many desired properties, such as convergence, improved time complexity, and more. Since the bounds are analytical, we can prune branches when going up the tree leaves to root as part of the planning session. Pruning is done by considering upper and lower bounds of sibling subtrees. Consider the left graph A. The last policy offers the greatest value, but it might have cost us a lot of time to learn it. On the other hand, if we had fast to calculate bounds, and the bounds of the best policy were not overlapping with all other bounds, such as seen in graph C to the right, we could declare the last policy as the best one while saving valuable time. If the bounds do overlap, as depicted in B, we increment the simplification level, and by doing so, we tighten the bounds until we can prune all branches but one. We are promised we can do so since at the maximal finite simplification level, the bounds converge and are just the original reward. More formally, given a belief tree, our algorithm SetBSP, it goes leaves to root of the tree and calculates subtree value function upper and lower bounds. If the bounds do not overlap, we can safely prune all branches but the best one, and keep the recursion up the tree. We first study our differential entropy approximation bounds behavior. We compare them to different approximation and the ground truth entropy. Next, we experiment with continuous 2D light-dark problem, in which the agent starts with some initial belief and needs to get to a goal location. Light beacons are spread around to reduce the uncertainty. This is a passive setting for the bound study. Light beacons are depicted in bright light, and particles are depicted in yellow. Particles with bigger weight have hotter colors. The graphs show entropy ground truth, different approximation, and our bounds using increasing simplification level, left to right. Dashed lines are our upper and lower bounds, And you can see how they converge to the ground truth differential entropy approximation when simplification level rises. For the planning experiment, our baseline is a sparse sampling scheme. The reward function is a multi-objective distance to goal and differential entropy approximation. We consider two settings, setting 1 and setting 2, which is harder. This is the mentioned setting 2. Each time step, the agent plans into the future and moves in the world. We experiment with changing tree structure, horizon, and number of particles. Each table entry, we report the mean planning time throughout the scenario for the baseline, the left number, and for our approach, the right number. As we can see, our approach, while providing the exact same solution as the baseline, is significantly faster, leading to a factor of 4 speedup in some cases. The colored plots are scenario-specific simplification level histogram. It gives a glimpse into the tree and show how are the simplification levels in both settings. On the left, we have the harder setting 2, and on the right, the easier setting 1. Note how simplification levels in the easier setting 1 are lower, which settle with a greater speedup as seen in the table. More details and proofs can be found in the paper and supplementary manuscript. Please also see our follow-up work in which we show how we speed up a state-of-the-art Monte Carlo research-based framework for POMDP planning available on arXiv. Thank you for your time. I hope you will enjoy it.